This resource is the second in a 6-part series on exponents and logarithms. Part 1 defines exponents and logarithms. The exponent laws are defined, and justification for the exponent law of multiplication is provided. We consider how to transform between exponent notation and logarithmic notation and define 2 special bases for logarithms. Part 2 explores expanding and contracting logarithms. Multiple examples of each are provided. Part 3 demonstrates solving logarithmic equations, with examples provided. Part 4 considers solving exponential equations. A general solution method is provided, and examples are given. Part 5 delves into solving exponential growth equations, with examples. Part 6 looks at solving exponential decay equations, with special emphasis on half-life problems. Much like exponents, there are certain rules that allow us to simplify logarithms. In fact, the rules for logarithms work exactly like their counterparts for exponents. The first rule works for multiplication. It says that the log of a product equals the sum of the logs of the items you are multiplying. The second rule involves division. The log of a quotient is the same of the log of the dividend, the number you're dividing into, minus the log of the divisor, the number you are dividing by. The logarithm of a quantity raised to the power equals the power times the logarithm of the quantity. As an example for the multiplication rule, consider the common logarithm of 15. If the rule holds, then the common log of 15 should equal the common log of 5 plus the common log of 3. Using a scientific calculator and rounding to 3 decimal places, we find that the common log of 15 is 1.176. The common log of 5 is 0.699. And the common log of 3 is 0.477. Doing a quick check, 0.699 plus 0.477 does indeed equal 1.176, so the rule works. What about the rule for division? Does the natural logarithm of 5 equal the natural logarithm of 20 minus the natural logarithm of 4? Since 5 equals 20 divided by 4. Let's find out. To the nearest thousandth, the natural log of 5 is 1.609. The natural log of 20 is 2.996, and the natural log of 4 is 1.386. Subtracting and allowing for rounding error, the rule works because 2.996 minus 1.386 is very close to 1.609. What about the rule for exponents? Is the common logarithm of 100 raised to the 5th power the same as 5 times the common log of 100? The common log of 100 to the 5th power, which is 10 billion, is 10. The common log of 100 is 2. Since 10 does equal 5 times 2, the rule works. The idea of expanding logarithms is to transform the logarithm of something with multiple parts into multiple logarithms. Instead of having one logarithm, we will have multiple. This process was very useful in the days before calculators. It made involved calculations much more simple. When you need to expand a logarithm, you should work systematically. Separate apart any multiplications or divisions first. Next, worry about exponents. You need to be very careful about exponents and exactly what they apply to. For example, in 5x squared, the exponent only applies to the x. But in 5x squared, the exponent applies to both the 5 and the x. The logarithmic expansion would look different for the 2 examples. Suppose we wanted to expand the common logarithm of 5x squared. First, we recognize that the 5 is multiplied by the x squared. The first step of our expansion would be the log of 5 plus the log of x squared, since the log of a product is the same as the sum of the logs. We are not quite done. We can still simplify the log of x squared. The 2 that is the exponent becomes a coefficient for the log of x. Note that the 2 only goes in front of the log for x, since the only thing that was being squared was the x. So our final answer would be log of 5 plus 2 times the log of x. Now suppose we wanted to expand the natural logarithm of x to the 4th power over y to the 3rd power. First, we separate the natural log of the division into the subtraction of the natural log of the numerator minus the natural log of the denominator. We finish by dropping down the exponents in front of the appropriate natural logarithm. Therefore, the natural logarithm of x to the 4th power over y to the 3rd power is the same as 4 times the natural logarithm of x minus 3 times the natural logarithm of y. Sometimes we want to go the other direction. We have a string of logarithms with the same base, and we want to write it as a single logarithm. Spoiler alert, this will be necessary when solving logarithm equations. The process for contracting logarithms is straightforward. First, write down your logarithm with the appropriate base. Then, use any plus or minus signs as cues for how to set up what you are taking the log of. Next, put in your numbers and variables of which you are taking the logarithm. Finish by moving any exponents into position. Let's look at a few examples. Suppose we want to contract the base 2 logarithm of 7 plus 4 times the base 2 logarithm of x. First, we write the appropriate logarithm, the log base 2. Next, we recognize that the sum of the individual logarithms becomes a multiplication when we contract the logarithms. Since we had the log base 2 of 7 and the log base 2 of x, we realize that the 7 and x are the factors being multiplied in the contracted logarithm. The final touch is to move the 4 that was in front of the base 2 log of x and make it into the exponent 4x. So log base 2 of 7 plus 4 log base 2 of x equals log base 2 of 7x to the 4th power. Let's look at one more example. Suppose we want to contract 3 multiplied by the natural logarithm of x plus 8 times the natural logarithm of y minus the quantity 6 times the natural logarithm of w plus 5 times the natural logarithm of z. First, we know that we are working with the natural logarithm, so we write ln. Now we use our clues to set up what we are taking the natural logarithm of. We see a minus sign, so we know there is a division, and we can set up a fraction. There are also plus signs before and after the minus, so that means there will be multiplications in the numerator and in the denominator. Next, we can put in our variables. The natural logs of x and y were in front of the minus sign, so they go in the numerator. The natural logs of w and z were both being subtracted, so those variables go in the denominator. We finish by putting in the appropriate exponents. When we do so, we find that 3 multiplied by the natural logarithm of x plus 8 times the natural logarithm of y minus the quantity 6 times the natural logarithm of w plus 5 times the natural logarithm of z equals the natural logarithm of x to the 3rd power times y to the 8th power divided by w to the 6th power times z to the 5th power. Remember the three rules for logarithms. The log of a multiplication is the same as the sum of the logs of the factors. The log of a division equals the difference of the logs of the things being divided. The log of something raised to a power equals the power times the log of the base of the exponent. We can use these rules to either expand logarithms or to contract them, depending on the situation. One situation where we want to contract logarithms is in solving logarithmic equations. We will see this in the next resource in the series, so stay tuned.